My name's Liz Hurley. I'm a software engineer at CJ Affiliate. That's an affiliate marketing company here in Santa Barbara, which is to say that I'm a software engineer who works in advertising. And I came here to talk to you, as you can see, about data. And I'm not sure what you guys were thinking. On the face of it, it sounds really boring, but I hope to persuade you that it's not boring at all. That, in fact, data is the lifeblood of the internet, and it touches lives in every corner of the globe. Now, you might point out that globes don't have corners, so I'm not quite sure how that works. But in any case, I do believe that this ubiquitous need for data is driving the need for ever more people with skills in computer science, and in particular, in data science, big data, and data visualization. So let me explain. So, what is data, first of all? Well, data comes from the Latin plural noun, the singular form of which is datum, which means a thing given. It's literally a given. So, what does that mean in practical terms? Well, let's see how they describe it at Wesleyan University, where they have a course on data analytics and interpretation.
What do we really mean by data? Data are pieces of information about individuals organized into variables. By individuals, we mean a unit of observation. An observation, or a unit of observation, refers to a particular person or a particular object, any particular unit of observation within your study sample.
Okay, I hope you heard that, but it basically said data is a unit of observation. And in that researcher's example, her data set was about people and their smoking habits, which might be interesting for some research purposes. But think about it in the context of our internet and mobile connected lives. We are streaming units of observation around the internet every single day. Every time you sit down in front of your computer and go to the browser, open a web page, you're sending out several units of observation about you. Which browser you're using, which version of the browser, which device you're on, the IP address you're at, any of your cookies in your browser that are related to that domain. And then we go with our mobile devices, and we go about, and we have many apps. Take, for example, what units of observation Google Maps is collecting about you. Here's what Google Maps observed about me a few days ago. So beginning early in the morning, they observed that I drove about 2 miles to the athletic club. After a while there, they observed I drove home. Then after some time, they noticed I was cycling to go to work. I never told them I cycled a bike, but they observed that based on what I was doing, how I was moving. Then after some time, they observed me going downtown to get my lunch on my bike, back to CJ again, and then I cycled back home. Now, my family might be thrilled to have this kind of information in about 20 years' time when I'm wandering around Santa Barbara in my dotage and I can't remember where I am. But if you don't want Google following you around in this way for whatever reason, like privacy, turn off location history on your Google Maps app. But I didn't come here to talk about privacy, I came to talk about data, although the two are quite tightly related. So that was my mobile phone. We also have other devices at home, smart TVs. Some of us have an Alexa. We have cars, and not just self-driving cars, but a modern car nowadays. This past summer, my brother rented a car while on vacation, and it came with the bonus feature that every day he got an email from the car rental company telling him how good a driver he was. The car was sending out stats about his acceleration and braking and fuel consumption back to the car rental company, who were helpfully ranking him against the other drivers who rented cars from them at the same time. He was not one of their better drivers. So that's just to say that there's a lot of data streaming around out there all the time, and I haven't even mentioned images and videos yet. Just think about it. How much content do you upload on a weekly basis? Photos and videos. How much do your friends upload? Then think of all the people in the world who aren't your friends. How much content they're uploading. And then there are all the cats who are uploading their content. So it's really, it's hard to conceptualize how much stuff is up there. I don't know if any of you have heard of this website called Petite Tube. So it's a website, you go there and they will play for you a randomly chosen video from YouTube that has never been seen before. And after you see it, it will never be seen again because it won't show up on YouTube anymore. So there's just such a lot of data. How do we even talk about it? It's loads, it's heaps, it's plethora, buckets, oceans, mountains, lashings of data. But how much is it really? Well, here's a stat from 2 years ago, so we know that's out of date already. And it says that every day we create 2.5 quintillion bytes of data. What's a quintillion, I hear you ask? I'll tell you. A quintillion is 1,000 times 1,000 to the fifth power. So we get the word quintillion from the Latin for 5, which is cinque, and it's 1,000 times 1,000 to the fifth power. In the same way, we get the words we have for million, billion, trillion, and quadrillion. Of course, we are in data science or computer science, so we don't usually refer to data storage in terms of 2.5 million bytes. We usually say 2.5 megabytes, or gigabytes, terabytes, petabytes, exabytes, zettabytes, yottabytes, and so on. More Latin, you say? No. These words are actually derived from Greek for some reason, I don't know why. But my point is, in helping us talk about these vast numbers, we resort to a linguistic framework that helps us articulate them. And in a similar way, in order to help us process and analyze vast amounts of data, we resort to a special technology framework that allows us to do this. And we refer to that technology as big data technology. So if you look back to our researcher earlier with her data set of people and their smoking habits, she probably had a few thousand, maybe tens of thousands of samples. And that size data set, that will work just fine in your bog standard laptop with a spreadsheet program. But if you try to analyze a day's worth of clickstream data on your bog standard laptop, it'll probably choke. So over the past 10 to 15 years, big data technologies have evolved that allow us to analyze and process massive amounts of data efficiently and affordably. Big data technologies is a very broad subject, so I'm not going to go into it much in today's talk. But I will just say this for it. Here you see some of the names and logos of some of the better known big data technologies. And as you're looking at this, you might wonder to yourself, well, are we talking about big data or are we talking about Pokemon? And I didn't make that up, by the way. You can Google for big data or Pokemon. There's a website out there where you can take a quiz. They'll pop up the name of a big data technology or a Pokemon character, and you get to figure out which is which. So now that we know we can actually handle all this data, what are we going to actually do with it? How can we make use of it? How can we derive meaning from it? One of the more effective ways of deriving meaning from data is to find a clever way to visualize it. And we call this data visualization. This is nothing new to you guys. You've been seeing things like these line charts since you were in grade school. There are bar charts. There are pie charts, like this one showing climate conditions in Egypt. So data visualization is nothing new, and nor does it solely belong to big data. But big data emphasizes the need for getting even more effective insights from our data. Some of the more effective data visualizations have been around for a long time. And this is one of my favorite examples. It's from 1869. And this is a map of Napoleon's campaign in Russia from 1812. It was drawn up by a French civil engineer. And when I say campaign, in this case, it wasn't an election campaign. Napoleon wasn't going for votes. This was waging war. Although, given our most recent election campaign, that's not a lot different. But in any case, what this map shows is the light brown stream that you can see here are Napoleon's troops as they made their way eastwards toward Moscow. The black stream are the troops returning. The width of the stream reflects the number of troops. 422,000 went out and 10,000 returned. Without knowing much more about the history, you can tell that this was a disaster. So this graphic is remarkable because it manages to show us in just 2 dimensions about 6 different kinds of data. We have the number of troops, we have the direction of travel, we have the geography, starting out here in what's modern-day Lithuania, over to Moscow. And we also have the width of the troops showing, the width of the stream showing the numbers of troops. And you can see that where there have been significant drops in troop numbers correlates to some significant drops in temperatures as well. These troops were only prepared for a summer campaign, let alone the very harsh winter that they actually encountered. So this tragic event is illustrated here with painful clarity. Coming back to modern times, a kind of data set we have today that we used to have hundreds of years ago is recommender data. Things like people who bought this book also bought that book. Or in Netflix, people who like this movie also like these other movies. And we often look at recommender data in a graph such as this, which shows the nodes, or vertices, and lines connecting the nodes. The lines are also called edges. And this can be a helpful way to look at this data, up to a certain point, beyond which it gets quite difficult to understand anything from the data. So here is an interesting approach to rendering graph data by a product called GMAP, which has nothing to do with Google Maps, I should point out. And this is actually a rendition of the graph data from people who bought Harry Potter and the Sorcerer's Stone, also bought whatever. So they actually render the graph data in a geographic map. So how they do this is they take the graph data and embed it into a 2D plane, and then they run a clustering algorithm on the data, which geometrically locates the books in the same cluster closer together, and the ones that are in different clusters are slightly removed from them. So in that way, they can infer where the boundaries might occur, the geographic boundaries might occur between the different book clusters. So you can see here that in Potterland, you can't see, but I'll send your teacher a link to this so you can drill down and you can actually zoom in. The books that are in Potterland also include things like Artemis Fowl series and Septimus Heap. And then you have what they call Rear Diania, which is Percy Jackson and his stories. And then different countries, the Stinkville and the Wangdoodle Land are for books for younger readers. So it just gives you an interesting way of looking at related data. You can imagine applying it to other domains, like I've seen it to TV shows or musical tastes. And it also has the effect of you can end up with features like peninsulas and islands. So it's kind of fun to see, which countries end up being neighbors and who might end up in an island. So that's GMAP. It's just a fun way to look at graph data. So those were two examples of static visualizations. But we're programmers, so we know how to change the data or change the picture when the data changes. Some of you guys have been doing this already using processing in Java. And there's a library that I like called D3 for JavaScript. And here's an interesting visualization using that library. What we have here is a bubble chart. And each bubble is a country. The size of the bubble represents the population of the country. On the x-axis, we have income per capita, which is an indicator of the wealth of that country. On the y, we have life expectancy, an indicator of the health of the country. Now, the time dimension here is encoded in the mouse over. And as I mouse over from the 1800s up to modern day, you can see how the health and wealth of those countries are changing. Sometimes gradually, sometimes there's a big bump, and you might think, oh, I wonder, what does that correlate to? There's probably some significant event in history that took place there, World War II or the rise of communist China or something. And then you end up all the way over here in modern times, and thankfully our life expectancy has increased. If you observed, it began way down in the 30s and 40s, and now we're happily up here in the 70s and 80s. Okay. So we barely scratched the surface of what data can mean in today's world. And as for what it can mean in the future, that's up to people like you guys. I understand why, for some people, the idea of a career in computer science might not be very appealing. Oh, for some of you, it sounds great. I get to sit in an office all day and stare at a screen and write code.
Yes.
And for some of you, it sounds like a nightmare. I get to sit in an office all day and stare at a screen and write code. So perhaps you have your passion lies somewhere else, in something totally, totally different. I would just
Disease
say,
prevention.
if you are one of these people whose passion lies elsewhere, there's another way to think about it. Advances and progress and development in any of these areas depends on masses of data. And to extract insights from this data depends on people with skills in computer science. So even if your dream career is not computer science, if it's something totally different, remember that the path to your dream career might go through computer science and data science and big data. That's all I had.